pick a number between from 1 to 100. Okay, mine's 50. I should pick a different number. 32. Okay. The current guess is 50. So the computer's trying to guess my number for me. So I said 32. I happen to know that 50 is too high, so I say too high. So he says 25. He's doing the bisection algorithm. Well, now he's too low. Snace is 37. I say, oh, you're too high. Snace is 31. Oh, he's too low. Snace is 34. Oh, no, he's too high. So he guessed it, 32. And so I click, you got it. And so he says, aha, I did it in only 5 tries. So it's the guess a number game in reverse, because I pick the number and the computer tries to guess my number. It's the bisection algorithm. And you know, it's bisection because it has to split the interval exactly in half. And that's going to be the most efficient way to go. Guess a number. Okay. Want to play again? Somebody guess a number.
14.
14. Okay, we're playing again now. It starts at 50. 14 is too high. 25 is too high. 13 is too low. 19 is too high. 16 is too high. 14. So I say, you got it. And you did it in 5 tries. So it's pretty consistent. Of course, if you guessed the number and it was 50, he'd get it right away. But that's not good. You want to pick numbers that he won't guess right away. Someone want to try again? I wonder if prime numbers would take longer. Pick a prime? Like 11 or 17? 17's a prime. So we'll play again. 17. That's too high. Too high. Too low. Too high. Too low. You got it. You did it in 5 tries. So I wonder if that's always going to be the case. Why would it always be 5? What's so special about 5? Well, what's 2 to the 5, right? 2 to 5 is like 32. So it's not like it's 128, which would be 2 to the 7, but it's pretty close. You know, if you think about it, it wouldn't need 7 tries in general. And I'm not sure exactly how you would get it to 7 tries. Suppose you said you wanted to do another number, and the number was 1. So we'll play again. So if the number's 1 and I say he's too high, and you got it, you did it in 6 tries. So that's probably your worst case scenario, is 6 tries. 2 to the 7 would be 128, and there's only 100 numbers in the whole thing, so 6 tries is probably the worst you're going to do. So it's nice to know what the worst case will be, but that only works out, that worst case estimation, when the number of numbers is known in advance. Then you just take log to the base 2 of the total number of numbers. But what if what you're trying to guess is a floating point number? Ah, that's different. Now the number of tries is not really very well known, because the number of significant figures could be quite large. If it's 17 significant figures, maybe it needs 32 tries or 30 tries. So it's a if you know, let's see, how many bits there are in the mantissa, that's probably about how many tries maximum you'd need, minus 1. And what did we say about the mantissa in a floating point double precision number? $52 bits. That's a lot of bits. That's a lot of tries. 50 tries for your worst case scenario, 50, 51 tries, a lot of tries. So this could take a long time to converge with a double precision number. But, on the other hand, you don't need a derivative. And you may not always have one available. So that's a rather large search space, the 52-bit mantissa search space. That's a big search space.
do the round?
Hmm?
I'm just thinking.
You want to try
I'm just
this
thinking
again?
how it rounded. Does it always round up?
Suppose, well, this is working with integers. Suppose we had this working where you're working with doubles. Get half. Get half is returning an integer. There's no reason why it couldn't return a double. And then this would be a double. And then the minimum and maximum would be doubles. And then, well, I guess the arguments to get half would have to be doubles. And what else is broken now that I've done this? This is going to have to be a double.
Oh, well, now that's...
Have I broken it badly here? H has now got to be a double. Oh, all the minimum and maximums all have to be doubles. I've never done it before, so obviously I have to correct the errors as I go. So now we can do the program again, only this time with double precision. In other words, pick a number between 1 and 100. 3.141592653589792238466. Okay. I picked pi. Let's see, he says it's 50.5. Well, he's too high. Oh, wait a minute. His guess is not formatting. That's too high. Too high, too high. Too high, too low. Ah, so he's converging. But he hasn't gotten to pi yet, because it's 3.1, so he's too high. That's too low. And that's too high. And that's too low. And that's too low.
You already guessed 3.1, you said 2.
3.14, right? Oh, did I pick the wrong? I told it to look in the wrong interval. Yeah. My bad. Play again. I wanted to. So it's really too high here. Wait a minute. Play again. I've got to pay more attention to what I'm doing here. So you guys help me out. 50 is too high. That's too high. That's too high. That's too high. That's too high. Now that's too low, right? I'm trying to go for pi, 3.14. How long is this going to take to converge? Right now it's too high. That's too low. 3.14, it's still too low. That's too high. That's still too high, right? That's still too high. But that's too low. So we're getting there. Now I've got an extra significant figure. It took a while, right? 3.1415. So he's too high. 3.1415 is still too high. Now he's too low. So now I got another significant figure. It's going to take a while to converge, right? Floating point number of convergence on this is going to be 3.1415. That's too low, right? And now I'm working on the next significant figure, too high. Now it's too low, 3.1415. We're getting there. We've got another significant figure. Let's say that's good enough. Now we can stop. Close enough. So you got it in only 19 tries. Wow. Now I'm thinking that I can keep going with this for a while. And if it takes me a couple or 3 tries for each significant figure, and there's 17 of them, this could take a while with a capital A. Right? And so that's one of those things that now all of a sudden speed of convergence becomes rather important for. I never played guess a number with a floating point number, but all of a sudden it makes sense. This is going to take a while. And you play it as a guessing game like this because it lets you, it drives home the point. How tortured you can be if you have to listen to the professor every time he says, oh, you're too low, oh, you're too high. Plus there's a computation involved in evaluating the formula that determines whether you're too low or too high. So far, that's just been a constant comparison. But if what you're trying to do is f of x and find out where it's equal to 0, and the computation of f of x is large because you're doing a lot of computations to do the computational, what does it mean? F of x could be a polynomial, could have many powers. We don't know how hard it is to compute f of x. So each try could take a substantial amount of time. That is computer time. What do you think of that? I can show you where this is at in case you're interested in playing with it. It's in my chapter 19 under observables. So you can play your own friendly game of guess a number, if you like that sort of thing. Oh, great fun. Let's play guess a number. Suppose, and this is kind of interesting, suppose you wanted to, I guess this is recordings, that's all good. You wanted to find a way to evaluate an arbitrary function. One thing you could do here is define an interface, right? Yeah, so here's a one-dimensional interface of one function, an interface that involves one variable. And so now if I can find a way to implement this evaluate function, I can write a whole host of different, I'll call them framework-based numeric computation routines that can deal with implementors of the interface function. If you don't know the implementation, but you can write functions that find write procedures that find the roots for these kind of general functions, then it's an example of a kind of design. What kind of design is it? Any idea? When you design your code and you don't know what the shape of the implementation will be, it could be any one of many shapes. It's an example of many, poly, many shapes, polymorphism. That's what this is. So when you're writing interfaces that could be implemented in any one of a number of different ways, that's an example of polymorphic code. If you want to see where something like this is used, you mouse right on the function and click on Find Usages. And then you can see where the functions are being used. Here's one for doing integration. Here's one for parsing functions. Here's one for finding derivatives. Here's one for finding roots. And here's the bisection algorithm, where you pass in a root, or you pass in a function. And now with bisection, we already know how that works, right? Because it's an interval search technology. So you repeatedly evaluate the function. In this case, you use the relative precision that's the close enough, and you look for a tolerance, and when it's close enough, you return your answer. And so now you can use X to do your guess, and you can continue to bisect. This is the bisection part. Bisect the interval, where X is the value that you're searching for, and so you keep looking to see when the value for X is close enough, and when it is, you return it. And now if you want to see who uses it, hopefully you can find an example. No usage is found. Oh, too bad. I should probably write a usage. Shouldn't be too hard to write a usage. Let's see if there's a main method in here. There isn't. Well, you definitely need a test. Public static void main string args array. And what we'll do here is we'll write a function using a local definition. So my function f is equal to new function, and we'll define it as a nested inner interface. And what it'll do is it'll return x times x. Is that a good one? Or maybe we could do this one. Math dot, let's see what we got. SQRT of x. There. So now we've got a function that does square root. So now what we'll do is we'll call bisection. We'll pass in the function f. We'll put in the number we're trying to find the square root of. Let's say it's 2. Computation tolerance for 0.002. Input send, and we'll print s out, Control J, enter, and we'll print out ANS. Let's see what that does. Run. Couldn't find it. I think he's looking for the place where it's equal to 0. Is the square root of 0 defined? I don't think it is. Might be. So if the interval is between 2 and 4, that's not going to find the answer. What if we go between minus, well, let's see, between 0 and 4. Yeah, you can't find it. So we need a different function to do a search for. Let's try x squared plus 4. And we'll search between 0 and 10. Do our run. Let's see if this works. Not a number. Let's just make sure I understand how to use this. It's going to find the root of the function. I think I need to do something a little bit like this. Minus 5. I think the root's going to be at 0. No, it's having troubles. What if I just put x in there? Oh. Well, that's a relatively small number. So he found it was equal to 0 at, or close enough to 0 at that tolerance. If I increase the tolerance somewhat, not a number. Huh. It stops pretty quick. So now if I say it's 10x plus, 10 times x plus 20. So what should the range be? The x-intersect, it should be, I would think, let's just pick a large range. So there, it found I found a root at minus 1.9. So now if I get my calculator, and I say something like 10 times minus 1.9 is minus 19.99. Let's see, minus 19.99 plus 20 equals, so it's nearly 0. So he's finding the root. In fact, if you wanted to, you could probably do something like this. 19.99115,943, and then he says plus 20 equals, so did I forget the my negative sign? I think I must have done, because minus 40 equals, there you go. So it's pretty cool. He's doing a root finding. Now what you could do on his way to finding the root is you could print out the iterations guess each time he goes through it. So you can see how many guesses there are. Quote x equals n quote plus x. And now when we go through and look for the root, you can see all of the iterations needed to arrive at the answer using bisection algorithm. Pretty cool. Now you can, because of polymorphism, reuse the bisection algorithm with an arbitrary function. You could have it be something like x times x. Or 10 times x plus 15, or perhaps minus 15 times x. So now you got a little quadratic expression. Now probably you know another way to find the roots in a quadratic expression. I guess this has to go a little further. Maybe this has to go back a little bit. Not a number. Why is that, I wonder? Has anybody done the root computation on this already? It's sometimes polynomials don't intersect the line. If that's the case, then that's the reason why this isn't going to intersect. Oh, maybe if I just take off the bias. Well, for some reason, this is not behaving well. It really should converge. There you go. Converged rather quickly there. I wonder if I've gotten too far out of range here. He's really having a hard time. Something about these quadratics that's really bothering my little program here. But that's okay. There's got to be a bug in here somewhere. Because when he says not a number, that return comes back because there was no convergence in the maximum number of iterations. The maximum number of iterations, that can be increased. You could make this as large as you like. Here's max iterations. Oh, it has to converge in 15 iterations. Oh, that's no fair. Let's make it converge in 150 iterations. Big science, right? There you go. So now if you're going to converge, see it does take longer to do convergence, obviously. So somewhere in here, I guess I could add a little bit more complexity and let it take longer to do convergence. Nope, that didn't help. Huh. Wonder why. X times x, bisections is double. It shouldn't blow up or anything. Well, you'd have to run through the code and find out where the bug is, for sure. Hey, we could make that a whole assignment. Great fun. So that's what I wanted to do, to talk a little bit about these basic ideas behind the ALU. And what I thought was interesting about the ALU ideas and the bisection algorithm is how it impacts the design of A to D converters. And A to D converters are the way we get into the computer from the analog world. Has everybody had a chance to learn about A to D converters in their first digital design class? Kristen, did they cover A to D converters in Digital Design 1?
I think so. Did they tell?
No. Oh boy, you guys need it. So let's get out of this. Let's see, if I hit F10.